Among the three main components of wood, paper industry mainly exploits the cellulose fraction, which implicates the removal and loss of lignin and hemicellulose polymers in the mill effluent. However, these fractions constitute interesting renewable sources of aromatic compounds and sugars, so the current tendency is to valorize them into new bio-based products in the so-called wood biorefineries. WoodZymes project, funded by the Bio-Based Industry Joint Undertaking, has been devoted to contribute to the full exploitation of wood biomass through the collaborative work of 11 partners from 4 European countries. The project goal was to develop tailor-made enzymes able to work under the extreme operation conditions of pH and temperature commonly utilized by the wood processing industries, including kraft pulp mills, where the predominant technology for paper pulp production is used. The new extremophilic enzymes and extremozyme-based processes aim to provide high-value bioequivalents of petroleum-derived chemicals. Here, we're going to tell you all about the most promising results obtained during the project. By two different approaches, screening of databases and protein engineering, WoodZymes partners were able to find and develop a set of new thermotolerant and alkaliphilic enzymes. Chylinases acting on hemicelluloses and laccases acting on lignin. Extremophilic fungal laccases engineered at CIB by directed evolution and bacterial laccases obtained by Metgen prove their impact on modifying kraft lignin, which is only soluble in an alkaline medium. Furthermore, Yatta and Metgen identified chylinases with outstanding extremophilic properties. The most prominent Metgen laccase and Yatta chylinase reach industrial and high pilot scale production using Metgen's enzyme platform. Kraft lignins isolated by CTP from the black liquors of Fiber Excellence and Navigator pulp mills were enzymatically fractioned using Megnin technology. The resulting wide range of lignin-derived fractions with decreasing molecular weight were chemically analyzed by Ernest, CTP, and Metgen. The lignin-based fractions were evaluated by Suprema and FCBA as components of polyurethane insulation foams, with up to 50% substitution of oil-based polyols. All the lignin samples were compliant with foaming requirements, although deeper optimization is needed to bring the technology to larger scale. The new extremophilic laccases were also tested by FCBA in the manufacture of medium-density fiberboards, in collaboration with Finsa. The applications of the enzymes had a positive, although limited, effect on energy savings during defibering of wood chips. WoodZymes lignins were used by FCBA also as a phenol substituent for the preparation of lignin phenol formaldehyde resol resins that were chemically analyzed by Ernest. The use of lignin fractions obtained through Metnin process enabled to decrease the phenol and formaldehyde content of the resins, being this effect more pronounced in the presence of laccase. The WoodZymes LPF resins resulted to be highly suitable as adhesive for plywood panels, presenting much better water resistance than previously reported ones. In the case of pulp bleaching, the use of the new extremozymes in the kraft pulp bleaching sequence allowed reducing the chlorine dioxide charge and, consequently, the bleaching effluent load of organochlorinated compounds. In particular, the use of the most prominent chylinase developed and patented by Yatta enabled up to 25% chlorine dioxide savings during eucalyptus kraft pulp bleaching at pilot scale. Fiber characteristics and pulp mechanical properties were not affected by the enzymatic treatment. Introduction of the most extremophilic chylinase before the oxygen delignification or bleaching stages of kraft pulps enables to recover more sugars in the effluents. However, isolation of hemicelluloses from fully bleached kraft pulps using alkaline treatments and extremophilic enzymes permitted to recover a greater amount of highly pure hemicelluloses. These sugars were evaluated in two different applications, as refining aids and binders during paper making, and for the synthesis of amphiphilic polymers. Cationized hemicelluloses allow significant energy savings during paper refining and notably improve the paper sheet mechanical and physical properties. Moreover, it was shown that the paper sheets could be recycled, preserving the enhanced properties. To sum up, WoodZymes project facilitates a new interconnection between the pulp and paper industry, enzyme technology providers, and fiberboard and insulation product manufacturers. These will result in increased competitiveness of European kraft pulp biorefineries, facilitating the industrial exploitation of all components of the biomass feedstock in several end-user applications. We have shown that the adoption of clean and environmentally sound technologies based on extrumozymes leads to energy and chemical savings in the wood conversion sector. Still, final environmental and economic performance analysis of the WoodZymes approaches will help to better identify the benefits compared to the conventional processes and suggest further improvements of the technology.